All right, so the last time we met, so we finished by talking about the cause of the seasons. So now we're going to continue on with the second video part of the video lecture for chapter 5. And let's start by talking about convection cells. If you understand how convection cells work, then we can understand how heat moves through both air and water. All right, so very quickly, right, when air is heated and water, generally speaking, it expands, becomes less dense, it goes up, and then it cools. As it cools, it contracts and comes down. And so that is a convection cell. If we take a look at this picture here, what causes this in the atmosphere? Of course, well, the sun is the driving force of this, right? So the sun's rays, they have energy in them, right? Once they strike something, that then is often converted to heat. So as the sun's rays strike the planet, it heats it up, that heats the air, right? That air then expands because it's heated, it becomes less dense. And if we take a look right here, right, that hot air, and again, if there is moisture in it, it brings that up into the air, into the sky with it, right? It rises, and of course, as it gets further and further up, higher and higher, it gets cooler. And so then as it cools, it will then contract. Cold air cannot hold on to as much water vapor, so it will drop it as precipitation, right? Snow or whatever. All right, once it's released that, then of course we now have cool, dry air. And then that cool, dry air is more dense, so of course it's going to sink down. As it gets closer to the surface, it'll warm up, and then we have this, nice little convection cell, convection current here. Okay, so here's a video to kind of help you visualize this process. All right, so we can see this big container of water here. That's cool. We're going to put some food coloring in this water here, and then we're going to heat it up, and let's see what happens.
In fact, I'm going to put a lot of food coloring.
I'm actually going to pause for a second here and turn off that sound. All right, here we go. So putting food coloring in. So we have water here that's cool or cold. We're going to put this heated water into the bottom, right? We put the food coloring in there just so now we can more easily see how it moves. So think about it. When this goes in, let me do this. I'll let it play a little bit more. There it goes. Remember, this is heated water down here. It's just red, so we can see it more easily. What do you predict as it flows out of here? What's it going to do? Is it going to stay here? Is it going to sink to the bottom or rise to the top? Take a guess. All right. What do you think is going to happen? Let's see. We can see that it is rising up, and the question is, why is it doing that? Well, it's doing that because it is less dense. As it's heated, the molecules move a little bit apart from each other, and it's less dense. We have this nice, heated area of water that floats on top. Again, why? Because it's less dense. Now, the same sort of thing. This actually happens, sort of, we'll say in the atmosphere, meaning the idea that as it's heated, it's going to rise up. But of course, as you get further away from the further away from the earth, it's going to get cooler and cooler, then eventually it'll sink down. But in water, we see this happening where it will collect and just sort of float at the top. As a matter of fact, we'll talk more about this at another day, but if you've ever been in a lake swimming in the summertime, you have all this nice warm water up top. If you ever dive down, you can get to a point where all of a sudden you hit very cold water, and it can be shocking sometimes. Like, wow, why is all this cold water down here? Because this area, this layer of warm water kind of floats on top. right? And again, why is it floating on top? Well, because it's warmer. All right, so let's keep going with this. And then it can do something else happen here. Of course, in this experiment, the heat is the source flame. Summertime, of course, from the sun. All right, now we can see here he's placed, he or she, I think it's a he, right, has put an ice cube. It's going to cool this water right here. What would you expect to happen to the water as it's cooled right here? If you had a guess, well, let's see if you're right. Look at that, right away. You see it's sinking. So the cold water is going to now sink to the bottom. Right. Again, the food coloring helps us see this. But of course, this happens in our atmosphere as the warm air rises, then it cools, it sinks down. Okay. Good deal. So if we understand this concept, this will help us understand what we're going to talk about next. All right. So again, global air circulation is affected by the properties of air, water, and land. So again, as the heated air rises and it cools, it sinks, we can have set up a system of convection cells. So heat and moisture are distributed over the Earth's surface by vertical currents, which form 6 giant convection cells at different latitudes. So notice 1, 2, 3, 4, 5, 6. Okay. Notice at some places the air rises. And again, where is it going to rise? Well, where it's warmest, especially at the equator. So as it goes up, right, it brings that moisture with it. As it gets up higher, it then cools and the moisture will condense and rain down. So that's why we have rainforests at the equator. Then that dry, cool air then goes this way, and then it sinks down at 30 degrees north, 30 degrees south. And as it descends, remember, it's going to get warmer, but remember it's dry. And so that dryness can actually pull moisture out of the ground. And so at 30 degrees north and south, we can have deserts. And also at the poles, air is very cold. So of course, it's going to be more dense, and they're going to be moving away. And then these two kind of collide together. It forces the air up. They're up again. As it goes up higher, it's going to rain down as the moisture condenses. Okay, so let me show you this. All right, so if we take a look at the planet, we'll see definitely at the equator, right? Remember, if we take a look at this number down here, we can see the latitude. At 0 is the equator. And if we were to go around, we see nice and green, right? As you go over to Africa, same thing, around the equator. Look at how green it is here. But remember, at 30 degrees north, so as we go up higher, you can see it's about 30 up here. Again, so if you can imagine the air goes up and then it descends down, as it goes up, I should say, here, and then it condenses, rains down here. There's lots and lots of rain. That cooled and dry air then descends down at 30 degrees north and south, and it's very dry. And so we have deserts often located at 30 degrees north and south. So if you go to the south here too, we can see 30 degrees down here, very dry as well. Okay, but also if we look around the globe at the equator, again, same thing, we can see how green it is. All right, so let me show you this little animation that will kind of help you also visualize this. Oh, I'm sorry, I just realized you were looking at the wrong thing. Very quickly, again, at the equator, as we go around the globe, we can see how green it is. Up here at 30 degrees north and 30 degrees south, we can see how dry it is, right? And as we go around the globe, right, we can see it nice and green at the equator. So let me show you this animation that will help you visualize this a little bit better. All righty, here we go.
The sun's rays are less spread out in equatorial regions.
Let me turn the sound back on. Sorry about that.
The sun's rays are less spread out in equatorial regions than in higher latitude regions. At the equator, air near the Earth's surface is warmed. it expands and it begins to rise. As the air rises and moves away from the equator, it cools. At about 30 degrees north or south, the air, now cooler and denser, sinks back to the Earth's surface. Some of the air flows back toward the equator, and some toward the poles. At about 60 degrees, the air flowing toward the poles collides with cold air moving away from the poles. The collision of these two air currents forces air upward, where it moves toward the poles and back toward the mid-latitudes. This pattern of global air circulation gives rise to differences in rainfall at different latitudes. As air rises, it loses its capacity to hold moisture. As a result, rainfall is highest at latitudes where air rises and lowest at latitudes where it sinks. This is why rainforests are found at the equator, evergreen forests at or around 60 degrees north latitude, and deserts at around 30 degrees north and south latitude. Deciduous forests and grasslands thrive in areas with intermediate levels of rainfall. Thus, the uneven heating of the Earth by the sun sets in motion the Earth's global air circulation. This leads to latitudinal differences in heat and moisture, which determine the distribution of the Earth's biomes.
Okay, so let's get a little more practice at that. We'll use this one here. So we'll kind of do this together. So imagine where at the equator, where the sun is hitting most direct, of course, the air will be moving up, right? And so which of these would show the arrow going up in this box? And if you're guessing this one, let's do this, right? And then, of course, this one is going up this way and fall back that way. So that would be this one here. Okay. The air is going down, and almost you could imagine if you took water and you kind of threw it at the ground, it's going to splash out like this. So air descending down, right? Make sure I'm on the right one here. Air descending down, some will go this way and some will go that way. So in this box, it's going to be going in this direction, right? So you're thinking this one, all right? And same thing, as this one goes down, some of it will splash that way, and some of that air will go this way, right? So we want one that's going in this direction, and that would be this arrow here, or this loop here. All right, air is coldest at the poles, and so it's going to be moving away. It's going to collide with this air mass and go up. So we're going to look for a loop over there that's going in this direction. You can ask yourself, which one would that be? Are you thinking this one? All right. And then this one, again, the air is just moving away. It's going to collide and go up, and then it's going to go in this direction here. So which of these loops, if you're thinking this one here, all right, we got it. So next, where air is going up, it's bringing the moisture up with it. It then will condensate and rain down. So where do we get the clouds, right? Any place the air is moving up. So we can see it's moving up here, so we're going to put that here. You can also see at 60 degrees north, it's also going up. So we're going to put some clouds there, because where the air moves up, remember, it's bringing that moisture with it. It gets colder and colder. It condenses and rains down. Same thing here at 60 degrees south, it's going up, right? So we're going to rain there. All right, remember, this air that went up, it rained down. So now it's dry air and cooler air. It's going to sink down over here, right? And it's going to pull that moisture out of the ground. And of course, that'd be a cactus. At 30 degrees north, and same thing here, where the air descends down, 30 degrees south, we have deserts. And it all kind of flows in motion there. All right, good job. Okay, so hopefully that helped you visualize this process. All right, so next, right, ocean currents distributing heat and nutrients around the globe. Remember, the Earth is one big open system, and the currents in the oceans help distribute that heat, and that's a good thing, and nutrients. Right, so take a look at the bottom here. Ocean currents influence climate by distributing heat from place to place and mixing and distributing nutrients. Okay. All right, also, not only does water hold on to heat and distribute it. But in our atmosphere, we have certain gases that we understand also trap and hold onto heat for a certain amount of time. And that's a good thing. The Earth would be much colder if we did not have these greenhouse gases in them. And we call them a greenhouse gas sort of for this reason. All right, so if we imagine that here's our sun, right? And this is a greenhouse. What happens in a greenhouse? Well, the sun's rays go right through the glass, right? And it strikes things like the floor or the plants or whatever's in there, the person, right? It's then converted to heat. And the heat wants to escape, but the glass traps that in. And so this greenhouse effect, right? It lets the sun's rays in, but helps trap the heat in too. This would be very similar to the effect maybe you had in your car on a hot day, right? Let's say you park someplace, it's very sunny, you roll up the windows, you close the door, right? You go inside wherever you're going, you come back, let's say an hour later, you open up the door and you know what's waiting for you, right? It is so hot inside the car. Now imagine this. Here's a neat idea to consider, right? It might be 90 degrees outside, but it could be 110, 120 or inside. Like it's hotter inside the car's not running, than it is outside. Like what's going on? Well, of course, what's happening is all that solar radiation, right? All that energy is traveling, is going through the windshield, the window, it's striking the seats, it's striking the dashboard, it's converted to heat, and the heat wants to leave the car, but you got the windows rolled up. So that keeps the heat in. So a similar concept, right? The greenhouse effect, or if you imagine it like the car window effect, we could call it that too. Sun's rays can get through, but the heat is being trapped in. So luckily for us, we do have these greenhouse gases in our atmosphere, like carbon dioxide, like methane, like water vapor, that when the sun's rays go through them, because they're transparent, it strikes the planet, the heat then wants to go right back out into space. And luckily, we do have these greenhouse gases that act kind of like a blanket and will actually hold on to some of that heat and also slowly release it. You don't want too much, you want just the right amount. And I kind of compare this to when you sleep at night, what is the perfect blanket that you use, whatever that is. Remember, you are the source of the heat, right? Your body. And so let's imagine that it's wintertime or whatever like that, but of course you're in your house and you accidentally, as you're sleeping, you kicked off all your covers. You wake up, how would you feel? Probably cold. Why? Because all your heat is just leaving your body and going into your bedroom, right? So then you pull over, let's say a thin sheet, and that's better, right? Because that sheet is going to keep in some of the heat, but it's still going to allow probably too much heat, right? And so, so again, a little bit is okay. It's better than nothing. But let's imagine the other scenario. Let's say someone played a trick on you, right? As you're sleeping, and they put, let's say, 6 sleeping bags on top of you. You'd wake up, right? You'd be so sweaty, like, oh my gosh, like what, And remember, the sleeping bags are not the source of the heat. You are, your body. What happened is that the sleeping bags trapped in more heat than you wanted. So the perfect blanket, if you have one, right, is the right size. So guess what? It traps in the right amount of heat, but also allows heat to escape so you don't get too hot. And we can kind of think of our atmosphere as at that point where it's just been the perfect level of keeping the right amount of heat in and letting the right amount of heat out. And so we've maintained certain temperatures for climate and so for things to evolve. So let me show you levels of different greenhouse gases here. All right, so here are some of the greenhouse gases that are in our atmosphere. And of course, like they're transparent or invisible to us. So, we can't see them with our eyes, we have to measure them with instruments. But we can see, for example, nitrous oxide, right, N2O. Denitrifying bacteria produce nitrous oxide in metabolism, so that's a natural source of it. Now, fertilizers and animal waste release enormous amounts, and this is especially the case for vast livestock feedlots. Methane, you can see, again, the dates. Now, of course, this graph is a bit old. Now, I'll show you a more updated one in just a second. Methane, termite activity and anaerobic bacteria living in swamps, landfills, stomachs of cattle, right, and other ruminants produce great amounts of methane. It's funny as it sounds, burping, farting, stuff like that, right? Decomposition. So there are natural and there's more man-made, like the landfill that will provide for more methane in the atmosphere. Okay, and also these all do not trap heat evenly or equally, I should say. Some are much more powerful, meaning they hold on to more heat than others. All right. Chlorofluorocarbons, or CFCs. Okay. Until restrictions were in place, CFCs were used widely in plastic foams, refrigerators, air conditioners, and industrial solvents. We'll talk more about these later, but at the time, they were these dream things, a product that we made that were very useful, and we loved using them until we found out that they were also destroying our ozone layer. We really said, boy, we got to stop using these. And not only do they destroy the ozone layer, but they're also a powerful greenhouse gas, which means, again, they trap in the heat. Okay. And then, of course, this last one that you've probably heard lots about are carbon dioxide levels. So again, there are natural sources of carbon dioxide, decomposition, forest fires, that sort of thing. But human caused is just really put this out of balance, we'll say, with the natural carbon dioxide cycle, especially burning of fossil fuels, right, and deforestation. So I want to show you something here, right, because this is kind of interesting. If we take a look at this graph, well, a couple of things are going on here. First, we can see that it only goes from 1960 to right here, so about the year 2000, and of course we're well past that, and we can see where it kind of levels off at 360. But I do want to point out this to you. Notice how it goes up and down every year, up and down, up and down. These are, again, carbon dioxide levels. We can see the overall trend definitely is up, but the question might be, why does it go up and down, right, each year like this? Think for a second, can you come up with any answer if somebody asked you that, right? Why is it going up and down every year? And let me show you something here. So if we take a look at the globe, this will kind of give us an answer. It turns out there's a lot more land mass in the northern hemisphere than there is the southern hemisphere. Okay, well, so what? Well, here's the deal. In the summertime, in the northern hemisphere, right, what's going on? Photosynthesis. Those plants are taking carbon dioxide out of the atmosphere, right? So the carbon dioxide levels goes down. And then in our summertime, the northern hemisphere, of course, it's winter in the southern hemisphere. Now, as we go to winter, of course, a lot of the plants go dormant, maybe they're covered with snow or whatever. So we just do not have as much photosynthesis going on. So they're going to be taking less carbon dioxide out of the atmosphere. But yet we're still burning, coal and oil. And so the carbon dioxide levels go back up again. And again, we could say, well, all right, southern hemisphere in the summertime, it's your opportunity now to do photosynthesis. But we'll see there's just not as much land mass here. So there's not as many plants taking the carbon dioxide out of the atmosphere, okay? So for that reason, we have this where it goes up and down. So again, it will go up when it's in the wintertime in the northern hemisphere, right? And then it goes down in the summertime as the plants are taking carbon dioxide out, and then up. But again, you'll see the overall trend is up because we are burning, of course, 365 days a year. Where are we now? Again, we could see where we were back in the 1960s, right? Less than 320. And we can see this ends around the year 2000. So again, where are we now? Well, this is one of those things that I hate to share this with people, right? I mean, look where we are now. We're at just the week of November 8th, it was at 412 parts per million. A year ago, it was 410. So we're seeing these, over 2 parts per million, almost 3 parts per million in just a year increase. From 10 years ago, it was 388. So, and again, this we can see how it, back last October, November, December, January, March, April, May, and then of course we start to see it come down again in the summer months as plants are doing photosynthesis. But we can see this October point here and the year prior to it. So it does not go down as far, right? Because we're still releasing so much carbon dioxide into the atmosphere. And remember, the big idea here is that carbon dioxide is a greenhouse gas. All right, so if we were to plot this though over a longer period of time, this is what it looks like. So just kind of look at this. Again, up and down every year, but there's just no, I don't even say debate about it. There's just the carbon dioxide levels are going up, and it is a greenhouse gas, meaning that's going to trap in more heat. And the vast majority of scientists are very concerned about this. Why? Well, if this is a gas that traps in more heat, if there's more of that gas present, won't it trap in more heat? It's kind of like saying, well, if the blanket traps in heat, if you put extra blankets on, will that trap in more heat and make you warmer? And I think you probably would say, yes, that would make sense. And so for many scientists, they see this trend and they say, well, all this carbon dioxide is going to be trapping in more heat and have huge impacts. Some we have a pretty good idea about, others we're learning. As for example, the acidification of our waters as the carbon dioxide dissolves in the water. But clearly we see, warmer water temperatures and warmer atmospheric temperatures on average as well. And we will talk more about climate change later, but again, just the general idea that we understand and we want a greenhouse effect. We want the right amount of greenhouse gases in our atmosphere. As the amount of greenhouse gases, those things that trap in heat, increase, the scientists are telling us, and maybe some say logic tells us that would trap in more heat and have an effect on our climate. Okay, and then those extra greenhouse gases in particular, right, and not only, but in particular carbon dioxide, can lead to what some people have called global warming, but I would say that is a term that has confused a lot of people, because some people think, well, wait a minute, there's snow in the wintertime, so clearly it's not warming. And so, it's not what we're saying, that there's never going to be snow or anything. Well, the bigger idea is global climate change. That's probably the better term, because that's less confusing to people. It's not that it's going to be warm everywhere. It's that it will change the climate in lots of ways. And we're going to talk about El Nino in just a moment, but in some ways, what you'll find out is that warmer water way down by South America during certain years, warmer water evaporates more, right? So as you have more water in the atmosphere, guess what? All that moisture comes up to us and you can actually get a lot more snow because the water is much warmer way to the south, right? And so it's this global climate change. So, but let me just kind of read this to you here, right? Global warming or climate change, considerable scientific evidence and climate models indicate that large inputs of greenhouse gases from anthropogenic activities. Now, what is anthropogenic? That is a fancy way of saying human-made activities, in particular, burning fossil fuels. All right, so again, large inputs of greenhouse gases from anthropogenic activities in the troposphere can enhance the natural greenhouse effect and change the Earth's climate in your lifetime. So some people would say, well, boy, you know, in the future, your children are really going to be seeing a problem with this. And many scientists are saying, if you're not seeing the difference right now or the effect, you're not paying attention. So for example, this is a new story just was released, published November 11th of this year. And we can see that the 2020 Atlantic hurricane season officially has the most named storms on record. Warmer water will evaporate more. And then you have more water in the atmosphere, and that will then cause more rain. And the warmer the water, it feeds more intense storms. So again, this idea of people saying, well, maybe in the future we'll see changes. Some say we are already seeing the effects. And the question is, if we just keep going like we're going, some of these very intense storms that have been unusual might be maybe the new normal, and that's what people are concerned about. Alrighty, so how do currents affect regional climates? So without the warm Gulf Stream ocean current, Western Europe would be subarctic. So let me show you this, right? So to go in closer. So as I mentioned already, let's see if I can find it here. There we go. So, right, water around the equator is much warmer, right? Because you have this intense sunlight, and the direction of the current basically goes up here, and then it goes this way. Okay. So, and as it goes, it's releasing that again, water will hold on to heat better than air, right? And so as it goes, it moves this current, moves that warmth, that heat to the northern parts, and it releases this to the atmosphere. And look how much more to the north these countries are, right, than us. We know in our area, where we are, the more to the north we go, it gets cooler, and that should happen over here too. But again, the reason it's not is because this Gulf Stream is bringing this relatively warm water over to it and releases that heat. Now, once the heat is released, of course, it becomes colder, and then that water will sink. And so as the surface water is going this way and then it releases the heat, it then sinks down. It's like a conveyor belt, and it will go in different directions. And this conveyor belt will distribute the heat and the nutrients around the globe. Okay, so now I'm going to share with you a couple of videos about the ocean currents and how they work.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, the tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds on to heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow, or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them.
Okay, let me show you one more to help you kind of visualize this. All right, and this is the Gulf Stream explained.
The ocean conveyor belt and the Gulf Stream. Ocean currents have a direct influence on our lives. They determine our weather, our climate, and much more. The ocean currents and wind systems transport heat from the equator to the poles and operate like a large engine for the global climate. In the oceans, there are numerous currents. The so-called ocean conveyor belt is very important for our climate. This term describes a combination of currents that result in 4 of the 5 global oceans exchanging water with each other. They form a worldwide circulation system. The conveyor belt is also called the thermohaline circulation, with thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. That is where the Gulf Stream begins. The Gulf Stream is very important for the European climate. Its length of 10,000 kilometers makes it one of the largest and fastest ocean currents on Earth, and it's very warm. At roughly 2 meters a second, it brings up to 100 million cubic meters of water per second towards Europe. A constantly blowing wind, the southeast trade wind, drives warm surface water to the northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius. The turning of the Earth and the west winds then direct the Gulf Stream towards Europe and split it up. One part flows south, another east to the Canary Current.
And also just want to make the point that, yes, this water is warm down here. And yes, as it goes this way, it's not as warm, right? Don't misunderstand and think, well, this is hot water. It's not. But remember, let's just make up a number. If it's 50 degrees Fahrenheit, right, that's much warmer than 32 degrees Fahrenheit, right? So there's heat in that water that will then keep this northern part of Europe much warmer than it should be. Okay, so again, it's relative heat. Don't think that this, because it's red, like this is hot water or warm water. Okay.
And a third part flows north, where it releases a lot of heat into the atmosphere as the North Atlantic Current. The water becomes colder there. Its salt content and density rise on account of evaporation, and it drops down between Greenland, Norway, and Iceland. There we also find the largest waterfall on Earth, the so-called chimneys, roughly 15-kilometer wide pillars with water falling up to 4,000 meters. 17 million cubic meters of water per second, or roughly 15 times more water than is carried by all the rivers in the world. This creates a strong maelstrom which constantly pulls in new water and is the reason that the Gulf Stream moves towards Europe. Countless species use the Gulf Stream as a means of transport on their trips from the Caribbean to northern areas. But it doesn't just bring us animals. An enormous quantity of warm air also comes with it. In order to produce the same heat which it brings to the shores of Europe, we would need 1 million nuclear power plants. That's why we also call the Gulf Stream a heat pump. Without it, the temperature would be significantly colder here, at least 5 to 10 degrees. Instead of lush fields, we would have long winters and sparse ice-covered landscapes in Europe. In the last few years, scientists and pundits in the media have repeatedly expressed the fear that the Gulf Stream could come to a standstill due to climate change. Because if the polar caps actually melt, the salt content in the water off Greenland would fall, as would its density. The North Atlantic Current would no longer be heavy enough, and so it wouldn't sink as usual. In the worst case, that would bring the Gulf Stream, our heat pump, to a stop. Some climate experts also assume that climate change could compensate for this effect. We know that it can be normal for the climate to change by looking at the development of the Earth over the last few million years. There are ice ages and warm periods. In the last ice age, a gigantic flood of melting water crippled the heat-bringing North Atlantic Current, covering the northern hemisphere in ice. Scientists have different views on the impact that climate change will have on the global ocean conveyor belt. But one thing is clear: when the climate changes, then the complex system of ocean currents and winds, which has remained fairly stable since the last ice age, will change in ways that we don't yet understand.
Right. So the last part, what he was talking about there, is during the last ice age, we had, glaciers, right where you're sitting right now, a mile thick of ice. It's incredible, right? Carved out the Great Lakes and everything. Well, as it was melting, we had a large amount of fresh water, but we had an ice dam. And then when that finally broke apart, all this fresh water rushed in. And what we believed happened is it stopped that conveyor belt from bringing warm water to Europe. So ironically, as the glaciers were melting, because we were coming out of it was actually warming up, right? So the ice was melting, that fresh water flows in, stops the warm water from going to Europe. And so then Europe, well, what effect would that have on Europe? Think about it. If that warm water stopped flowing that way, it went colder. So the ironic part of this is, right, as it was the cause of the warming, which was the melting, actually stopped this and made it colder in Europe. And that's the reason why we like to talk about global climate change than just global warming, right? Right now, we're very concerned with Greenland. we see large fissures in it. There are scientists there studying it. We see huge amounts of water melting and running off. And if something similar were to happen in Greenland, where if it were to lots big chunks break off water, that too could then stop potentially. That's the concern. That would stop this conveyor belt or very slow it down. And then again, see what's happening here, right? This idea that the warming that is melting the ice could actually then make it colder in Europe, right? Global climate change. Now, again, why would it be colder? Because normally that warm water, that conveyor belt brings that warmth up here, right, to this northern area. But again, because of that warmth, it melts the ice and that flows in, that could stop that. And so then it gets colder in Europe. But at the same time, remember, if this warm water can't move, it's just going to keep getting warmer and warmer. So areas down here might actually get a lot warmer. And warmer water causes more rainstorms. And so again, global climate change, it's very, some of it's predictable, some of it's unpredictable of what could happen. But overall, it's just change. And remember, species have evolved over a long period of time to the biomes they live in. And if this change happens too quickly, it's unlikely that many will be able to evolve quick enough to those conditions. And it's very chaotic. So again, without the warm Gulf Stream ocean current, Western Europe would be subarctic. And then this idea of an upwelling. Normal trade winds blow offshore, pushing surface water away from land, which is replaced by cold, nutrient-rich bottom water. All right, and nutrients and upwelling support aquatic food chains. And I tell you what, we will stop here today and we'll pick up with this with our next video.